In this section we're looking at differential equations with related rates. So this moves us back to that section where we looked at related rates, so using the chain rule to find different differential quantities. And this time, because we now know how to solve differential equations, we can actually solve the equations that we get. So in this example you've got the variables y, x and t. We know that dx dt equals tan t, and we also know that y equals 3x. Now the question part A is asking us to find dy dt as a function of t. Now the first thing we can see here is we don't have a dy dt. We have a dx dt, which would help us get the dt on the bottom, but we don't have any dy anywhere. And we know with related rates that what we need to do is use the information we already have. So if we take y equals 3x, you can see we've got a relationship there that involves y. If we diff this, we're going to end up with dy dx equals the derivative of 3x is 3. So we get dy dx equals 3. Now we're interested in finding dy dt, which means we'd have to have the dy on the top, and that's linked with the dx, and we'd have to have the dt on the bottom. So that's going to be dx over dt. We have both of those quantities, and the cool thing is that the dx on the bottom and the dx on the top, they actually disappear to give you what you require, which is dy dt. So that means that dy dt equals dy dx, which is 3 times dx dt, which is tan t. So dy dt equals 3 lots of tan t. And if you wanted to get rid of the multiply in there, I'll get rid of the multiply. So you can see, you could simply write it like this. Alright, the next part of the question is asking us to find the solution of the resulting differential equation. So part B. So what we're going to do here is we're going to solve, let's do this in red, solve dy dt equals 3 tan t. And to do that, what we can do is integrate, we could integrate both sides. I'm actually going to do this with the separation method. So I'm going to take the dt over to this side, so we get dy equals 3 tan t dt. I'm then going to integrate both sides. There's a 1 implied there. So we have y equals the integral of, and in fact, take the 3 out the front. It's a bit easier to work with. The integral of tan t is the same as the integral of sine t over cos t. And this is going to be a substitution integral. Let's go to the next page. Let's bring this over. It's a substitution integral because you can let one of the things here be u, and if you differentiate one of those functions with respect to t, you're going to be able to eliminate the other function. When you do this, you're always going to end up with the function that you can eliminate on the bottom. So you'd want to pick u as cos t, because that way when we differentiate du dt, we get sine cos is negative sine t, which implies that dt equals, bring that up and bring the negative sine t underneath, du over negative sine t. So you can see the thing we're going to eliminate ends up underneath. The two equations in the boxes are the ones we use for our substitutions now. So we now have y equals 3 times the integral of sine t over cos t is now u, and the dt is now du over negative sine t. So we can cross those out. We end up with 3 times the integral of 1 over u du, and the negative, I'm going to bring that out the front there. So that negative underneath, bring it out the front. So we have negative 3, integral of u, 1 over u is log u, plus c. So that's the solution that we end up with, and because we want this to be y as a function of t, that makes sense with what we started with. We had dy dt. We're going to just substitute the u back in. So it's going to be negative 3 log of cos t in a modulus sign as well, just to make sure that that's always positive. So that's our solution to our original differential equation here. And we got that differential equation using related rates. So using the link between dx dt and dy dx to get dy dt, and then solving it using here a separation method to get your integral, and then a substitution method to actually solve that integral.